Hello everyone, I'm Professor Harrison, and welcome back to our module on regression analysis. Today we're going to be covering the classical assumptions behind ordinary least squares, and the result that ties them all together, the Gauss-Markov theorem. We're following Margot, a graduate student trying to reassemble a story her family buried. Today she's fitting an example fund's returns against the market, and what she really wants to know is when she can trust the slope that comes back. She turns to the next problem in her coursework. Regression will always hand you back a slope and an intercept. You give it data, it gives you the numbers. But that raises a real question. Out of all the ways you could possibly draw the line through a cloud of points, why should we trust that the one that ordinary least squares picks is the correct one? The answer is that under a specific set of conditions, OLS isn't just a reasonable choice, it's actually provably the best choice. Those conditions are called the classical assumptions, and the result that makes them matter is called the Gauss-Markov theorem. To understand what these assumptions are and why they matter, let's anchor all of this into one example and keep coming back to it. Margot takes a fund's monthly return and regresses it on the market return over the same month. The slope of that line is the fund's beta, and it tells you how much the fund tends to move for every 1% that the market moves. And the error term, the part that doesn't sit on the line, is everything about the fund's return that the market doesn't explain. So with that picture in mind, here are the conditions that we need. The first assumption of OLS is linearity in the parameters. Basically, the model has to be a straight line combination of the things that we're estimating. The fund's return equals the intercept plus beta times the market return plus the error. One thing to notice about this is that it's an assumption about the parameters, not about the variables. We're actually allowed to bend the variables in any way we want. You could regress onto the market return squared if you wanted to. What you can't do is have beta multiplied by another coefficient, squared, or have it buried inside something that's nonlinear. As long as the piece that we're solving for enters linearly, OLS has something that it can work with. The second assumption is no perfect multicollinearity. In our market model, there's only one predictor, so that's something that won't really bite just yet. But it shows up the moment that you move to multiple regression, which we've already covered. It says that no predictor can be an exact linear copy of another. Imagine that Margot put the market return in as a predictor twice, once in percent and once in decimal form. Those two columns carry exactly the same information, so the regression can't decide how to split the credit between them, and the math ends up breaking. The fix is simple. Don't feed it redundant variables, and as long as each predictor brings something genuinely new, then you're fine. The third assumption is the big one, and it's called the zero conditional mean of the errors, and it says that no matter what the market does, the average of the error term is zero. Another way that people say this is that the predictor is exogenous. So pick any level of market return that you like, say a month where the market was up 3%, then across all the months like that, the part that the market doesn't explain should average out to zero. It shouldn't be systematically positive in up markets and systematically down in down markets. If it is, then the market return is secretly carrying information about the error, and the slope that OLS gives you is going to end up tangled with that. One common question is what could actually cause this to fail? The usual culprit is a variable that you've left out that's correlated with the one that you've kept. When this happens, it's called omitted variable bias, and we're going to get a little more into it later in the module. The fourth assumption is homoskedasticity. It's a long word, but it's a very simple idea. It says that the spread of the errors is the same no matter what the market is doing. Here's where it tends to fail with return data. In calm months, fund returns tend to sit very close to the line. In turbulent months, they can scatter all over the place. So the error variance isn't constant. It's small in quiet markets and large in volatile ones. When that happens, we call it heteroskedasticity, and it's extremely common in finance. The line itself can still be perfectly fine. It's our sense of how precise the slope is that ends up being thrown off. The fifth assumption is no autocorrelation. The errors in different months shouldn't be related to one another. Knowing the fund's surprise this month shouldn't tell you anything about the surprise next month. This is really a time series concern, and with monthly fund data, it's easy to picture a violation. If the fund tends to drift in the same direction for a few months in a row, then this month's error and last month's error are going to move together, and that's autocorrelation. Like before, this doesn't end up changing our estimate of the slope, but it does change how precise we believe that estimate is. There's a sixth assumption that's a little bit different from the rest. It's optional, and it says the errors follow a normal distribution. We don't actually need this for OLS to be a good estimator. In fact, the only time that this assumption is required is when there's a very small sample that you're looking at, and even then it's only going to affect things like your confidence intervals and your tests on the slope. We'll build out what that inference machinery looks like a little bit further into this module, And the assumption of normality is what makes it possible to do these inferences. So now let's get to the payoff. The Gauss-Markov theorem says that if the first 5 assumptions hold, then ordinary least squares is blue. That's an acronym. It's worth taking apart one letter at a time because each letter is a real claim. When we say that OLS is blue, we mean that it's the best linear unbiased estimator. Let's break all these down. E here stands for estimator and the L stands for linear. What this means is that our slope estimate is a linear estimator. This just means that we estimate our slope using a linear combination of the y values in the data. What exactly does that mean? Well, think back to when we derived the formula for the slope using matrix notation. We found that it was x prime x inverse x prime y. Note that we're using linear algebra here to define what our slope is going to be. Linear algebra just means linear combinations of data. All we're doing to estimate our slopes is linear combinations of the different y values here in the equation. Those combinations are derived by the x prime x inverse x prime part of this formula. Next, let's take a look at the U. U stands for unbiased, and unbiased means that on average across many samples, the estimator lands on the true value. If the real beta of the fund ends up being 1.2, then the slope that you get from repeated samples don't systematically come out high or low. They center around 1.2. In symbols, the expected value of beta hat equals beta. Margot only has one sample, of course, but unbiased tells her that the procedure itself isn't tilted in any particular direction. Then finally we get to B, which is the real prize. B here stands for best, and best has a pretty precise meaning. Among all the estimators that are both linear and unbiased, OLS has the smallest variance. We call that efficiency. So there might be other ways to estimate the slope that are also linear and also unbiased, but none of them are more precise than OLS. It ends up giving you the tightest, most reliable estimate in the whole class. So that's why OLS is the default. When those conditions hold, it's provably the best linear unbiased estimator that you can write down. The flip side of this is just as useful. Every one of these assumptions can also fail, and a couple of them, the constant spread one and the no carryover one, fail constantly with return data. Each break has its own diagnosis and its own fix, and that's really what the back half of this module is going to be about. Margot writes down the conditions as a checklist and tapes it above her desk. From here on, every regression in her investigation is going to hand her a slope and a standard error. Before she trusts any of them, she runs the list. The math always gives her a number. What she has now is a way to know whether she can trust the number or not. So that's the foundation under everything that we do in OLS. There's a specific set of conditions, the classical assumptions, and when they hold, the Gauss-Markov theorem promises that ordinary least squares is the best linear unbiased estimator. Unbiased means that it's centered on the truth, and best means nothing else in the class is more precise. So when those assumptions hold, reaching for OLS isn't just a habit, it's provably the right move. And when they don't, you know exactly which conditions you need to go check.